Sometimes the availability of buffer is considered to be default in a certain network. In such environments, marginal buffering is not an issue. So the overall treatment and analysis of the network is dependent upon how much transit time does a packet spend into the network. And that leads our discussion from marginal buffering to arbitrary buffering at every hop. Here, we shall look at first the definition of arbitrary buffering, what is its relationship to the leaky bucket algorithm that we have earlier studied, the buffering constraints which determine the overall transit time at every hop, and then we look at a scenario. This topic of arbitrary buffering is so interesting and much more practical as compared to marginal buffering. That is why we see that a lot of attention has been given to this particular topic. For instance, there is a paper, Switzerland, a QoS communication architecture for workstation clusters. It talks about arbitrary buffering, and it talks about a very interesting notion of using arbitrary buffering support and the marginal utility that is obtained out of it. It means how much benefit are we getting by deploying memory and storage capability in the network. The next paper by Phil Lewis is The Emergency of Network Abstraction and Techniques in TinyOS. And lastly, our very often referenced book, Communication Networking: An Analytical Approach by Anurag Kumar. Formally, arbitrary buffering means the arrival of the packets at the port of a switch, a multiplexer, or a router in a random way where there is support of buffering. So if there are already buffered packets, it means first in, first out behavior would be observed. If there is no packet in the buffer already, then the arriving packet would be treated right away. And if there are multiple flows, then there would be competition amongst the flows in occupying this buffer. If the buffer overflows, then the packet drop comes in action. So the relationship between buffer availability and call admission becomes very interesting. It is governed by leaky bucket algorithm because if you remember, leaky bucket included the overall bucket size, the token rate in the token bucket algorithm, and the packet size. Of course, the leaky bucket algorithm has a very strong relationship with ensuring QoS for various flows. When we look at buffering, it does not come without any cost. For instance, if an arriving stream is admitted into the network, what will happen to the traffic already being carried and stored at the input port queue of the devices? And if it were a single communication channel, such as a multiplexer connected directly to a demultiplexer, the problem still was relatively simpler. But in a multi-hop network, the problem becomes more exacerbated. Why? Because if the router, which is deep into the network, has some kind of congestion or slows down, so its buffer is going to overflow, and it would have a backscatter or backtracking effect on the previous routers, and eventually the first router connected to the source is going to be affected, leading to overall throttling of data rate by the sender. Let's look at a multi-hop arbitrary buffering scenario, and then we'd see how multiple flows affect each other. Looking at the same example that we had earlier seen in marginal buffering, here We take specific sources such as voice at location 1. If it is destined for location 2, leaves the network at location 1, enters into router R1 and leaves for router R2. Similarly, if there is voice destined for location 3 from location 1, it has to go through router R2. So at R2, 2-hop traffic is multiplexed from location 2 to location 3. It means that the independent visualization of the traffic coming from two independent sources is now merged. So what we conclude is that if we have traffic that is coming from a single source, if we know the buffer availability, we can determine the buffer occupancy. It can be well identified and characterized because we would exactly know when the packets from a single source enter and leave the network. However, as we have just seen in the scenario, after multiplexing is done at the first hop, now the flows have become dependent. So can we look at this situation as two interdependent flows or a new flow with sources which are two different networks? But if we are looking at it as a single flow, then its behavior would be different. This kind of interdependent relationship in a multi-hop network is difficult to characterize, and especially when you are looking at the simulation results, you can draw intuitive results from that. But mathematical treatment of it becomes quite cumbersome.